Everyone, my name is Sophie Trentafilidou and I'm one of the vice presidents on the IS&T board of directors. I want to welcome you to the fourth in IS&T's new seminar series featuring best student research from electronic imaging 2020. This series showcases the research by students that led to the best paper and best student paper awards received earlier this year. I would like to take a moment to thank an individual donor who wishes to remain anonymous and the Imaging Science Group of the Royal Photographic Society for supporting this program. Their support will help us provide electronic imaging registration grants and ensure the continuation of this online seminar series, which has been pretty successful so far. I also want to thank HP for their support of the Best Paper Award for the Imaging and Multimedia Analytics in a Web and Mobile World Conference that included today's paper. Before we begin, I would like to take a couple of minutes to tell you about IS&T and the Electronic Imaging Symposium in particular. For those not familiar with the Society of Imaging Science and Technology, IS&T is unique in that it brings together nearly an equal number of international researchers and practitioners from industry and academia. This makes it a great place for students to showcase their work to prospective employers, for those in industry to learn about exciting developments in imaging research. IS&T spans imaging across applications from capture through processing to output to vision. Our conferences, courses, and journals offer a place to share the latest innovations with a network of others who have a love for and curiosity about the world of imaging. IS&T's breadth is best found at the Electronic Imaging Symposium, where 20 conferences and more than 25 courses over everything from AR, VR, and autonomous vehicles to big data, remote imaging, and mobile devices. Two great features about electronic imaging are the open access proceedings and the ability to submit a journal paper, which of course gives you a journal citation in lieu of a proceedings paper and still give a talk. For those who haven't heard, Electronic Imaging 2021 will be held online. The Electronic Imaging Symposium and conference committees are working as we speak now to construct a program that offers the same great papers from academia and industry, with many opportunities to connect, communicate, and network as you would in person. Focusing on ways for people to interact is a high priority as we plan 2021 electronic imaging. Electronic imaging can be quite overwhelming for those who don't know it, but it's a great place to learn about the ways the fundamental science and technology explored in the academic settings can be incorporated into products and improve our world. For students, it offers registration grants, a student young professional research showcase, a demonstration session, which is a bit like show and tell, conference-based paper awards, and the ability to take courses for free. We encourage you to explore what electronic imaging has to offer and to submit relevant research to it. Now, as part of our efforts to provide more value to students, we've launched this seminar series this summer to highlight best paper research, allow people to learn about areas of imaging outside their subfield, and provide a space to talk more in depth about the technology area specifically. Our goal is to make the program interactive. So after today's talk, we will open the floor to discussion and not just QAs. So please feel free to engage and be part of this conversation. The actual seminar hour slot depends very much on your contributions too, which will make it alive. So to facilitate this, please take a few minutes to rename yourself, if you can, on Zoom, to your first and last name plus your affiliation, as this will help all of us to get to know each other while we're talking. We would also like you to turn your camera on if possible, if not now, when we move to the discussion part of the program. Now it gives me a great pleasure to introduce Bryan Blakeslee, a recent graduate of Rochester Institute of Technology's Computer Engineering program, whose areas of interest are deep learning and embedded systems. Bryan will talk about a new and novel deep architecture for programming pixel-level directional change detection based on a 4-class classification scheme. Bryan, to you. Bryan, you're muted. We can't hear you.
Sorry about that.
That's fine.
My name is Bryan Blakeslee, and this is LambdaNet, a fully convolutional architecture for directional change detection. So first off, what is change detection? It is the automated enumeration of differences between pairs of images. There's a wide variety of applications for this, including fault detection in manufacturing, where you can compare a reference part to a newly manufactured part, disaster management, where you can prioritize the allocation of resources by, say, damage to individual homes, or crop monitoring, such as searching a field for blight as compared to a known healthy reference field, or aerial surveying where you're monitoring for geologic changes to a local area. Change detection itself breaks down into two different categories. You have structured change detection and unstructured change detection. Under structured change detection, you're looking primarily for changes with respect to specific classes of objects, such as a person in the context of a security application where you're looking for people entering and leaving an office, or maybe monitoring an airfield looking for aircraft that have been moved from their landing pads. Now, in the unstructured paradigm, we remove that class-based distinction, and we focus on any change, really. These can still be physical objects like people or cars, or it could be more general, such as landscape changes from deforestation. And you can see that here in these images from high-altitude aircraft. There's a region of the field here which has been completely harvested of crops and is now barren. So there's a few different ways that you can actually implement change detection, but one of the most interesting techniques is basically Siamese networks. Siamese networks take the form of encoders, usually pre-trained on a particular data set like ImageNet with shared parameters. In this particular instance, the output of the encoders are fed into a decision network, which is the part of the network that's actually trained. That network just emits basically a single bit, either a change or a no change event for a particular pair of reference images. Now you can take this to the most logical extreme where you replace the decision network with a full VGG style decoder that allows you to label in a binary fashion the changes at the pixel level, enabling you to localize those within a specific region of the image. So in order to evaluate this particular LambdaNet, we opted for the Change Detection 2014 data set, which is a total of 53 videos split amongst 11 categories. We have a large variety in terms of both perspective and conditions, and it consists of both color and thermal videos. But most importantly, each individual frame in the video has an associated semantic segmentation ground truth map, which labels all of the example objects of interest in each of those frames. And here we have some samples of images from this data set where you have your image on the left and the associated ground truth mask. Black indicates a region of no change, while white indicates particular changes of interest. Several of the videos also have these large gray regions, which are effectively a don't care mask, for which there is no truth data available. And finally, we have just an overview showing the various types of videos that we have. We have various indoor-outdoor shots in inclement weather, sunshine. We have videos shot at night and, and also in the thermal spectrum as well. So then what actually is directional change? Current change detection schemes utilize a binary classification paradigm. They're only interested in marking whether a change has occurred, but they don't actually indicate whether an object was added or removed or exchanged with another object. So under directional change, you actually have a four-class labeling scheme whereby black constitutes no change, blue constitutes subtractive change, or a target of interest, or an object of interest has been removed from the reference image in the target frame. Red, which indicates additive change, or that an object of interest has been added into the target image from the reference frame. And then you have green, which indicates an exchange of objects between the reference and target images. So there's actually a relationship between binary change and directional change itself. And this is actual output from LambdaNet operating in either the binary and the directional change modes. And you can see in the binary mode where you have this rather complex change of a person moving from a standing position to a sitting position, you do correctly identify the binary change that took place. However, it's difficult to infer what actually took place in that mask. When you move to the directional change position, directional change output, you begin to see the individual outlines of the person in the sitting position and the person in the standing position. And it's actually possible to determine what portions of the image were altered in what manner. Now, if you flatten that directional change result, you actually end up going back to the binary case, indicating that directional change is really a mechanism by which you can take a binary change prediction and subsegment that according to what objects were added, removed, or exchanged. So in order to build a network that realizes this new paradigm, we need to borrow from a couple of existing areas, specifically semantic segmentation, where you do pixel level labeling utilizing convolution and deconvolution networks. And also you need the Res2Net module. This module is important because it allows for the detection of change targets of interest at multiple sizes in the image. And the way it works is by basically chaining and forking these convolutional kernels together to create a new activation map which has what's called multi-scale information. This at the X1, Y1 mapping here, you will have a scale of 1, a receptive field size of 1. However, when you move to Y2, X2 mapping, you have a receptive field size of 3. Now, at this fork, you end up merging the receptive field size of 3 with the prior activation map. This chains 2 convolutions together, giving you a receptive field size of 5, and then the pattern repeats to a receptive field size of 7. This lets you look for change targets that may be of slightly different sizes, or allow you to look at surrounding context to maybe determine how significant that change actually is. And when you put all of this together, you end up yielding the LambdaNet architecture, where you have a VGG encoder pre-trained on ImageNet in order to maximize the diversity of features that you actually extract. Then you examine that final feature layer with your Res2Net layers in order to convert that final representation into a multi-scale representation. Then you fuse those together via concatenation and pass them into another Res2Net layer before decoding it out to the actual difference segmentation via a ResNet decoder. Now, training proceeds exactly like it would for any other neural network. Your reference image is your past image, and your target image is your present image. And you feed those forward through the network to obtain your difference segmentation. You then evaluate the actual segmentation with a weighted cross-entropy loss, and then use that loss to backpropagate through the decoder portion and the multi-scale portions of the network in order to learn what is effectively a separation function that marks any like elements of the image as a no change region, and then splits out the significant changes according to their additive, subtractive, or exchange classes. So before we dive into the actual results, there are a couple of small caveats. The change detection 2014 data set is predominantly geared towards structured change detection. However, the goal of LambdaNet is to be able to detect both structured and unstructured changes. As a result, when we look at some of our evaluation metrics, LambdaNet actually ends up getting penalized in its evaluation scores for any kind of unstructured detection that it makes. Now, before we dive into the actual directional change results, I want to put up a couple of videos of LambdaNet operating in just the binary case. And here we have some badminton players playing on the court. And one thing that is actually of interest is when you have in your reference image these people down near the corners and edges of the image are actually segmented out in the prediction for the network. Second, if we restart this video briefly, you'll see that the video is actually quite jittery, and yet we're able to still adequately detect a number of significant changes in the video. That's particularly useful for any kind of, say, drone application where you might have that jitter naturally present in your video stream. Now, a much more interesting result from the binary case is what I call the bottles on the table. And what you'll see is this is a thermal video. This particular version of LambdaNet has never actually seen a thermal image before. And you can see that it does track the structural change of the girl on the table. However, it also picks up other changes that occur. I'm going to skip forward slightly here and pause it to show that LambdaNet is actually making a an additional prediction of change here that's not actually labeled in the data set. And what it's detecting is these bottles here on the table have actually been removed. Furthermore, it's also detecting that the reflection of the bottles in the rear mirror are also no longer present. So now let's actually look at some of our directional change results. Here, we'll start with just some of the simpler structural cases where we actually have specific targets of interest and we're attempting to find those in particular. And we can see here that we have an example of both additive change and subtractive change in the form of a man being added to the target frame and a woman being removed from that target frame. And we can see that the classes do actually line up as we would expect. This is a more complex instance of structured directional change where we're actually tracking a person sitting down. In this instance, we can not only see the fact that his head is lower in the target, the man's head is lower in the target image, resulting in a subtractive change, but also the fact that his arms and laptop are now out on the table, indicating an additive change. And then the remaining change that's actually segmented is the exchange region from his body shifting from the standing position to the sitting position. And then finally, we have some structured change from an overhead traffic shot. And we can see that not only do we properly identify the cars that are actually marked in the ground truth, but we actually successfully identify almost all of the traffic that has altered in the inside of the don't care region of the image. So then here we have some examples of more unstructured, excuse me. We have an example of a more unstructured type of detection. You have the bottles, again, being correctly marked, bottles and cans being correctly marked as additive change in the image, despite the fact that at no point do we ever actually train this network to specifically look for bottles. And so it is actually performing that separation function to highlight regions of the image that are dissimilar. And so here we just have the overview of the LambdaNet architecture. But for comparison, let's see what happens when we only operate with the encoders and we use a threshold to actually indicate our changes instead of the full decoder system. And what you see on the left is the binary mode of the threshold-based comparison. And you can see the threshold, we've tuned the threshold to get basically the best possible results for indicating that this man is a change of interest. Unfortunately, what you also see is a number of small spurious detections that are basically meaningless due to the trees blowing in the wind, as opposed to LambdaNet, which actually segments the individual correctly, but it also rejects many of those spurious changes from the leaves that would be not of interest to a human. But what happens when we give it images that are basically the same? The only real difference between these two image pairs here is that the tree branches have moved in the wind. And we can see that under these conditions, the threshold-based technique generates an immense number of false positive changes versus LambdaNet, which actually is almost entirely blank. And this is actually quite important because it means that LambdaNet is not only selecting for changes that are of significance, but it also has a built-in intuition of what is considered to be an insignificant change. And so it's able to prune many of those spurious detections from the output map. And as a result, we can actually see between the threshold and LambdaNet in the binary case, LambdaNet actually performs significantly better than just the raw threshold technique. Now, when we expand that to the directional change case, we see that the additive and subtractive change classes both compare favorably with the binary change case. However, the exchange class tends to suffer a little bit. And the reason for this is perhaps a little counterintuitive, but initially the reason for this is the mechanism by which an exchange was defined. When you look back to the definition of directional change, we explicitly define exchange as two objects of interest changing places. However, that's not the only case in which a potentially valid exchange can take place. You can actually have a valid exchange take place inside of a no change field, where say a object that is unmarked in your ground truth can take the place of another object. That will actually be marked as a correct, as an exchange, despite the fact that that exchange is not explicitly marked in the ground truth. That's not an issue with the network itself, but rather it is due to issues with how the change detection 2014 data set is actually labeled. And here we actually see kind of some issues with the don't care regions. Approximately a quarter of all videos have these very large don't care regions. And it leads to some issues with respect to how you label your targets of interest. The only really reasonable way to handle this is to set this field to a no change class. Unfortunately, this ends up confusing the network because this car would be considered by a human to be a change of interest, but it's going to be marked out as a no change in the ground truth due to these large don't care regions. Furthermore, targets of interest can actually enter and exit these don't care regions, meaning that you have many instances where the network learns incomplete representations of some of the more important targets. And we can see this in the directional change case where we overlay that don't care region. And you can see that the network actually segments quite well the portions of the car that are located in the region of interest. However, once it drifts, the segmentation drifts into the don't care region, then it begins to break down and develop some voids. One particular case where the network does not perform particularly well, however, is in the case where you have really, really strong illumination or glare. And you can see that because these cars here blend in so closely with the background, the network actually rejects them as significant changes. Meanwhile, this extremely bright flare from oncoming car's headlights gets tagged as a significant change. So overall, we've introduced directional change detection, which is capable of identifying additions, removals, and exchanges for both structured and unstructured changes. We've also presented the LambdaNet architecture, which consists of a Siamese network with Res2Net multi-scale layers, a residual decoder, and we've demonstrated that LambdaNet is both effective at binary and traditional binary and directional change detection. Thank you very much. Any questions?
Thank you so much, Bryan, for this very technical and very interesting paper. And of course, congratulations again for the award you received at the Electronic Imaging. I would like to ask you to stop sharing maybe your screen now, so that we can get back to gallery view and people can use the gallery view so that we can see each other. I would also remind those who are attending, if you want to put your cameras on, so we make this meeting as lively as possible and as real as possible, if we can say so. If you want to, if you have any questions, please raise your hand either using the participants buttons, or you can physically raise your hand or just throw any question you have. We aren't so many, so I don't think we will have any problems dealing with questions. So do you have any questions for Bryan? All right. So I will start with my own questions, Bryan. It seems that the LambdaNet has various differences from other methods of building around object detection and foreground background segmentation. Do you want maybe to discuss a little bit the most significant differences, capabilities between LambdaNet versus other change detection techniques built about object detection or foreground background segmentation?
Sure. When I was reviewing literature, what I found was a lot of unstructured change detection algorithms attempted to solve this problem via either just generalized object detection or via foreground background segmentation. And those methods are really, really great for pulling out specific objects of interest in an image. But the issue is that when you start comparing the outputs of those networks, these detectors will often pick up every single little object under the sun. And so you end up bombarding the user with all of this information regarding spurious detections that you have to sort through. And so the idea with LambdaNet was, and the multi-class distinction was, we know that these networks tend to learn specific classes of objects very well. And so by breaking the binary change detection class into multiple classes, you start to break down the learned representations of the network into things that are more abstract. And so the sort of ideal case would be to break those down to the point where LambdaNet is sort of a very, very intelligent, almost like blob detector, where you have, where you're not really looking for people, cars, bottles, things of that nature. You're looking for objects which possess characteristics that a person would consider significant. And so you can end up, I
get you, and that was very I mean, I guess is the most impressive element of it. And it's just, I'm sorry to interrupt you, but I think that it strikes those who are not very familiar with the work around, you know, your area. But it's a very clever thing. And I have more questions, but go ahead. Yes, yes.
That was basically it.
Yeah. So just on the same tune, and because it's in a way, this follows another question, is that so you talked about intuition, when the blobs are becoming meaningful. So it is, isn't it? So we need to distinguish somehow when the blobs becoming meaningful and become something, an object, isn't it? Or it become an object of interest. And this is, I guess, is application dependent.
It is somewhat application dependent. The goal with how the network was trained, it wasn't to try and condition it. It wasn't to try and condition the object to look for the specific objects that I was actually training on. It was to try and condition the network to say, here is an example of what we would consider significant. And this is why when you then train on, cars, people, boxes, things like that, then when you have the kid clearing the tables on the bottles, or clearing the bottles from the table, then you also have the bottles end up getting tagged as a significant change as well.
Sure, and that was very impressive. It just occurred me, the application, just to explain a little bit myself, when you had this outdoor scene with the trees moving, and obviously it was not a significant change because there were no people passing, no animals, nothing really changed about from the wind moving the trees. In some applications, this might be the point of interest. Of course, when you walk and try to locate objects as a human being or as a machine looking for objects, is not. But it's interesting what makes something important for the network and for the human, of course. We start with the human, but what makes something important for the network to pick up. And it's quite, impressive. Any questions in the meantime?
Yeah, I have a question.
Yeah.
Mark, so I have three questions. So the reference image, was that used in just the training of your networks initially, or is a reference image also used in the, once it's been trained, in the prediction phase of it?
The reference image is used in both training and the evaluation phases.
Okay, so how does it handle the case where your reference image is changing all the time? Like, let's say you have a drone or a self-driving car where the background is changing all the time.
So in that case, you would need to move away from using just an individual reference frame, and you would need a reference video as well. But that's really just a matter of just running. Basically, you would just take one. It would be, if you were present for Sanders' presentation, it would be just an instance of, you would need to, say, drive your car along that particular path in order to collect your reference video, and then you can synchronize that reference video against your target frames on your second pass through that environment.
Okay. Does LambdaNet have some sort of a sensitivity parameter where you can sort of tune it for like how big a blob you want to find? Like Sophie said, maybe you want to find the small little leaves changing, and I noticed in your river or lake or whatever it was, there was sort of a dark patch there. Maybe that would be of interest, and it didn't find it. So can you change your sensitivity?
Yes, you can. You can change the sensitivity in kind of a per class basis. It basically comes into the sensitivity comes in at the loss function, actually, where you use the weighted cross entropy. And so one of the initial issues with the network was it actually wasn't learning very well initially, and it was because the class imbalance was so great. And so if you wanted to become more sensitive to, say, additive change and subtractive changes, then there's a weighting term in the loss function that you can raise, and that will make it more sensitive to additive change or subtractive change or an exchange.
Okay. Sorry, Sophie, I forgot to introduce myself. I'm Mark Hayward. I work for the Procter & Gamble company, and I do custom image analysis programming full-time.
Thank you, Mark.
Oh, okay.
Well, and thank you, Mark, for your questions, also for chipping in. You had a third question, I believe. Is it? Are you doing?
Yeah, that was actually all of them. The whether the reference image was used, and then the sensitivity, and if it can handle camera panning or background changing.
Right, thank you. Any other questions? I have one more, Bryan, which is not dissimilar, in the same lines as Mark. So what are the challenges of using LambdaNet when using individual applications, say automotive, where we can see a lot of directional changes being very rapid, versus, say, crop change detection, where the changes are very gradual and in time, and not so distinct from moment to moment. So you know, they will change in days rather than in seconds.
Yeah, it is kind of application dependent. I think if you were taking images in, say, I think there's some, yeah, I think it comes down to a little bit of the sampling interval, in that if you have high speed.
Exactly. Is it simply down to sample interval, or there are other challenges? Essentially,
it should simply be down to sample interval.
Right.
It will take pretty much all of the images that it was tested on were images that the network had never seen before. And so it really should just be down to sampling interval. There should be no other issue, as long as if you're monitoring a very slow process, then you probably want a very long sampling interval, it'll pick that up just fine. But if you're doing a self-driving car, you know, potentially like 30, 60 hertz video.
The sampling interval is, I mean, there is a long conversation, because when do you want to detect the changes? At what point? You have to know, you know, how fine are the changes, etc. I just think whether it is, as I said, the question somehow follows Mark's question, how the subtleties that we need, and this of the changes that we need to see, plus the sampling interval. But
that brings up.
Yeah.
Oh, sorry,
yes,
that brings up another question. Actually, is like, how do you handle like color changes? Like, let's say you were looking at, you know, maybe it's a fixed scene, but now you have, you know, noon sunlight, or you have
in illumination.
The sunset, where you have more kind of a reddish thing. You know, a lot of times we'll put a color checker chart in there to compensate for that. But if colors are changing, is that something you detect or not detect?
So color changes do end up getting detected. I do have some results where it's shot in an office building that has a skylight, and because you can tell that the illumination level from the skylight varies because of clouds passing through, and you can actually, if you pick a static reference image, you will see that where the skylight is very, very dim, you'll actually see the patch on the ground of light, as it gets slowly brighter, slowly gets indicated as stronger and stronger change. So it is actually a significant part of what it does is actually related to color and intensity.
Right. Okay. Thank you, Bryan. Do we have anyone else who would like to chip in? All right. In this case, I will have to close the session. And thanks, Bryan, for his brilliant paper. Thank you, Mark, for your questions, and thanks to everyone for being here with us. I would like to remind you that we have another seminar scheduled in 15 days. The time is a little bit different because our speaker is from Japan. I can't remember the time, but it's on the IS&T website, and you will get emails, relevant emails. So thank you all, and I hope to see you in 15 days. Bye-bye.
Thank you. Bye.